Okay. I want to give you another example that's a little different. And this is really a very famous recurrence relation that goes back, oh my God, like 9 centuries. They're called the Fibonacci sequence. Okay, so the way it's defined is that f1 is equal to 1 and f2 is also equal to 1. So this gives me two base cases. Okay, notice that it's like when we do non-recursive, or rather when we do recursive definitions, some of the recursive definitions or defining equations don't depend on previous values. We call those base cases, and this is why. Okay, now here we have an induction step that depends on two previous values. Okay, so because we're depending on two previous values and not just the immediately preceding value, that's a pretty good hint that we're going to need something like complete or strong, right? Remember, those are just synonyms. Complete or strong induction, okay? Just plain mathematical induction doesn't help you when you're working with the Fibonacci numbers. Okay, so let's see. What do the Fibonacci numbers look like? Well, f1 is 1 by definition, f2 is 1 by definition, f3 is the sum of the previous two, so that's 1 plus 1, which is 2, f4, sum of the previous two, that's 2 plus 1, 3, f5, sum of the previous two, 3 plus 2, which is 5, f6, sum of the previous two, 5 plus 3, which is 8, f10, sum of the previous two, that's f of 9 plus f8. You know what? Trust me on this, that is 34 plus 21, which is 55. If you don't trust me, go ahead and figure it out yourselves. I applaud that, okay? I like that. I wrote a program to kind of enumerate it for me. Okay, so here is the fact. It's pretty obvious, right? F sub n is equal to 1 plus the square root of 5 quantity raised to the n minus 1 minus square root of 5 quantity raised to the n divided by 2 to the n times the square root of 5. Yeah. If you can actually see that, if that's obvious to you, oh my God, congratulations, okay? It's not obvious to me, okay? This is just a fact. It's something that I can look up because I know it exists. Let's prove that, okay? Remember, figuring this stuff out is harder to do than it is to prove. So we should be able to prove. So we're going to use induction, and we're going to need base cases because there are two bottoms in the Fibonacci definition. So in the case when n is equal to 1, okay, then we try it. f1 is equal to, well, this is according to the definition, is 1 plus square root of 5 minus 1 minus square root of 5 divided by 2 square roots of 5. Well, the 1 and the 1 cancel out. I get 2 square roots of 5 in the top, 2 square roots of 5 in the bottom. Those cancel. 1. Excellent. That is what f1 is. Okay, n is equal to 2. This gets a little uglier because I have 1 plus square root of 5 squared. Don't panic, right? We just use our algebra. That is 1 plus 2 times square roots of 5 plus 5. Then minus 1 minus 2 square roots of 5 plus 5. And what we need to do is to add those. And so the 1 and the minus 1 cancel. The 5 and the minus 5 cancel. 2 square roots of 5 plus 2 square roots of 5 is 4 square roots of 5, which conveniently is what we have in the denominator. So those cancel. That's equal to 1. Okay. Base cases are usually easy. Okay. Now let's look at the next case. Oh, that looks frightening. But it's just a whole bunch of arithmetic, okay? So f of n minus 1 plus f of n minus 2, this is just a recurrence relation, right? That's our first step. So then how do we get this? This is the induction hypothesis, right, for n minus 1. This is the induction hypothesis for n minus 2. We have to use both of those induction hypotheses because f of n is defined in terms of two smaller values. And we can do that because we're using strong induction. Okay. Now, like I said, once you get here, the rest is algebra. Okay. So I'm adding two fractions. So what I'm going to do is I'm going to combine those, right? And we have 2 to the n minus 1 times square root of 5, 2 to the n minus 2 times square root of 5. So what I'm going to do is I'm going to multiply this by 2 and multiply that by 2. Okay, and that way I can combine everything into the same denominator. So this is 1 plus square root of 5 n minus 2. That's going to move there 2 times. Minus this, that's going to move right here again 2 times. Okay, and the reason I moved them was because I was kind of trying to have the plus square roots of 5 and the minus square roots of 5 together. Okay, so let's combine these two. Well, shoot, this is actually 1 plus square root of 5, right? Times 1 plus square root of 5 to the n minus 2. Okay, so what I can do is I can actually just factor out the 1 plus square root of 5 to the n minus 2. That comes out here, right? And what I'm left is 1 plus square root of 5 plus 2. Well, that's just 3 plus square roots of 5. Okay, same trick here, except I have a minus sign, right? So I'm factoring out the 1 minus square root of 5 to the n minus 2, and I'm left with the 1 minus square root of 5 and the minus 2 case out. So that's what that becomes. Okay, great. And so now what am I going to do? Well, I have 3 plus square root of 5. I can treat that as 2 times 3 plus 2 times square root of 5 and then divide that by 2. I did the same here. So basically I multiplied the numerator by 2 and I multiplied the denominator by 2. So notice that n minus 1 became n, that's this times 2. And this comes from here, right? That is a times 2 operation. So numerator and denominator are multiplied by 2. Nice. So anyway, so now what are we going to do? Well, I still have 1 plus square root of 5 plus, and now how can I do this? Hey, wait a minute, right? I might actually be able to do some factoring here, okay? Because 6 plus 2 to the square root of 5, right? I claim that's equal to 1 plus square root of 5 squared, right? And you can go ahead and work it out, but that becomes 1 plus 2 times square root of 5 plus square root of 5 squared. That's plus 5. 1 plus 5 is 6. Yep, that's true, right? Likewise, this one is 1 minus square root of 5 squared. So now I can combine them. That's 1 plus square root of 5 to the n, 1 minus square root of 5 to the n. Isn't that what it was supposed to be, right? So yes, success, right? That's the actual value that I wanted, right? So it's tedious algebra. I cannot emphasize how tedious the algebra is, but that's the reason that you learn algebra in high school. That's the reason that you're tested on algebra before you can place. That placement exam that they do over in the math department, and yeah, it's just a necessity of life. I'm not asking you to love algebra. I don't love algebra. I'm just asking you to be able to do it, and I'm sure you are. So no problems there.